Well, hello and welcome to Math Blossoms, where growing in mathematics is natural. I'm your teacher, Miss G, and for today's lesson, we're going to learn how to solve literal equations. Let's get started. All right, what is a literal equation, you might be asking yourself? Literal equations, a literal equation is an equation with more than one variable, and many times the variable has an important characteristic, such as in a math formula. So the variables are always representative of something in real life. And sometimes we have to manipulate formulas to solve for certain things that they're asking for. For example, here's some equations you might see that are literal equations. Geometry formulas. So this one here on the left in green, that one's the area of a triangle formula, which is 1/2 times the base times the height. Now, if you're solving for a height, you might have to move some things around in this formula in order to isolate your h for a height, right? And that's what we're talking about when we're talking about literal equations. We're solving for a specific variable that's in the equation somewhere. The second equation in orange is how we convert Celsius temperature to Fahrenheit. And then the last one you may be familiar with, the one in blue, that is the volume of a cylinder formula, which we learned previously. We were studying volume. And there are some questions that were on your exam for this, which was solving for the radius, remember, or the height when given the volume. So let's do some practice on this, so maybe you can kind of understand how to work with these a little bit better. So for literal equations, similar as traditional equations where you often solve for one variable in terms of numbers using inverse operations or opposite operations, in a literal equation, you solve for one variable by using inverse operations to move the other variables as well. Okay, so here is a property that comes in handy when you're working with literal equations. And that is the commutative property. The commutative property is for addition and also for multiplication. And it just basically states that if you add two numbers together, you will get the same result, the same sum, if you switch those numbers around. For instance, 3 plus 5 is 8. Well, so is 5 plus 3. So if I move those numbers around, I'm still going to get the same sum. Whereas the product in a multiplication problem, the same thing can happen. 2 times 6 is 12, and so is 6 times 2. So it doesn't matter what order those numbers are in when it's add or multiply. You can move things around and still get the same answer. So sometimes you might end up using that property a little bit when you're working with literal equations. Let's try solving some literal equations. Okay, so for these equations, we may be moving variables around, adding and subtracting, or multiplying, dividing. I purposely left out distributive property and combine like terms. However, those can pop up in a literal equation, but you oftentimes don't see those. So I just made it simple so we can kind of see where what we're talking about and how to do these. Let's try using blue this time. I just feel like using blue. Okay, so for this one, they're asking us specifically to solve for x. So one thing about literal equations is they will ask you to solve for a specific variable. And literal equations have more than one variable. So this one has an x, an a, and a b, but we're solving for only x, which means we need to get x by itself. So similar to a regular equation, you're going to be doing these steps here. Well, we don't have an x on both sides of the equals, so we can skip the move variable step for now. And we're on add subtract. So what is being added to my x is the a. So I need to cancel that out first because our goal is to get x all by itself. So I need to get rid of this a, and I also need to get rid of that 2 that's next to the x as well. So when I subtract a from a, I get a 0. And then on this side, I'm going to also have to subtract a from this b. But since we don't know what those numbers represent, we don't know what b represents or what a represents, we're just going to write it like this, b minus a. Okay, because that's all we can do. We don't really know what that number is going to be because we don't know the value of b or the value of a. So when I rewrite my equation, I have 2 times x equals b minus a now. Okay, we've done our add subtract step just like a regular equation. And now we are going to do our multiply divide step. So what's being multiplied times my variable x is the 2. So to make that 1x, I need to divide, which is the inverse of multiply. And 2 divided by 2 is 1x. So we're just going to write that as an x. And then when I divide the b over a by 2, since I don't know the value of b or a, I'm simply going to write it as it looks, b minus a over 2. Another way you could write this equation would be x equals b over 2 minus a over 2. It's the same thing. This is the same thing as this here. So whichever way is easier, all of this could be answers. Okay, so let's try another one. This one over here, we'll switch colors. Let's do, we'll use a green this time. This time we're solving for a. So we need to get everything around the a to move to the other side of our literal equation here. And again, we have something being added to our ax here, and that's the b. So we're going to have to subtract that first. This time we are trying to get a by itself, right? So we do need to get rid of this. And when I subtract b from this side, I can write this as c plus d minus b. Okay, so c plus d, I'm going to put that in parentheses, minus b. Okay, c plus d minus b. And of course, if you do c plus d, you're going to do it in order anyway, and then minus b. So you could write it with or without a parentheses. It doesn't really matter on that one. And so now you've got a times x. Ooh, my a. Hang on, let me write that again. Strange. Okay. All right, so a x, and we don't have to write the b because it's gone. And then we could write c plus b, c plus d minus b. Okay. And the last step is the multiply divide step. There was no moving the variable or anything because we didn't have a's on both sides or anything. And so multiplying, the x is being multiplied times the a. We want the x to go away, so we're going to divide it by x. X divided by x is 1, and 1 times a is just a, which is what we want. And then we have to divide all of this by x as well. So we end up with a is equal to c plus d minus b over x. And just as in the first problem there, we could also write it like this: c over x plus d over x equal minus b over x. We could write it like that. I feel like that's a little bit harder to write out than just putting the whole thing over an x, right? But both of those would be the same type of thing. Okay, so now that we've done all of the steps for all of the problems, let's see. Oh, do I have another one on here? Let's see. Got another one going on. I do. So let me erase this one because I have this right here, which is s equals 4 times x. And they're asking us to solve for x this time. We're going to use, this orange here. And this one's kind of easy because the only thing we have to get rid of is the 4 because we want to isolate our x. So we just have to divide by 4 on both sides. And since we don't know what s is equal to, our answer is just going to be s divided by 4 is equal to x. S divided by 4 equals x. That's almost hard to say. Okay. All right. And then we have another one over here that we're going to do. So let me erase some of this. Okay, this one is, I should have made these go a little bit lower to the page, but that's all right. This one's 36 equals by, or b times y times x. And we're solving for y this time. So if I'm solving for y, that means I need everything to go away on the side of the equation where the y is, except for the y, right? So since b and x are being multiplied times the y, and because of the commutative property, I can rearrange this. I can say, okay, 36 is equal to bx y, right? And I can move those around because when you multiply, it doesn't matter what order they're in, they're going to get the same answer, right? 3 times 5 is the same as 5 times 3, right? So if I'm trying to get rid of this b and x and leave the y, I'm just going to divide all of this by b and x. That's going to give me, oops. Okay, that's a b, even though it doesn't look like it. That's going to give me a 1. Bx divided by bx is a 1. And 1y is just y. And I have to do that on the other side of the equation, 36 divided by bx. And which is my answer. Y is equal to 36 divided by bx, or b times x. Okay. And so that's just 4 examples of literal equations. Let's see some. Okay, let's try solving some literal equations that are geometry formulas. The first one we want to try is the area of a triangle. A equals 1/2 times b times h. And they're asking us to solve for the b, which means I have 2 things I need to eliminate, basically. And that's the 1/2 and the h. Okay, if you look at this formula, they're all being multiplied, 1/2 times b times h. So I will have to divide, which is the inverse of multiply, in order to cancel it out and rearrange this equation and get the solution for this literal equation. So we'll do that one later. So let me go ahead and get me a pen here. Okay, so if I'm going to divide 1/2 by 1/2 to cancel that out first, we know that 1/2 divided by 1/2 is 1. So any number divided by itself is just a 1. And we want it to be a 1 because we essentially want this to cancel out. 1 times b times h is just bh, right? And that's what we want. We want over here to just be the bh because we want to eliminate some things around this b in order to isolate the b. Now, when I divide on the other side by the 1/2, because we do have to do it on both sides, that's a little trickier. So I'm going to show my work over here so you can see what we're doing. A divided by 1/2. And so when you're doing this, you're going to have to remember how to divide by a fraction. And it's very easy. You just have to remember the keep, change, flip rule. The keep, change, flip rule states that when you are dividing by a fraction, you are basically multiplying times its reciprocal. So keep, change, flip says to keep the a the same, change your division to multiply, and then flip your fraction upside down to its reciprocal. And then just multiply across the top and across the bottom numerators. Well, since a is not in fraction form, we'll just place it over 1 to turn it into fraction form. A times 2, we write that as 2a. We typically write the number before the letter when we're multiplying. And then 1 times 1 is 1, and 2a over 1 is just 2a. Okay, so all of that work I'm showing you just to remind you how to divide by a fraction. And when you do that, you will get 2a on this side of the equation. Okay, so we've eliminated our 1/2 now. Now we need to get rid of the h. And again, it's being multiplied times the b. So I just need to divide by h to turn that into a 1. And we know b times 1 is just b. And then when I divide the 2a by h, I don't know the value or the numerical quantity of a. So that's all I can do is just write it as 2a divided by h. And that's essentially my answer because I have isolated my b. That's a b over there. And I have basically solving a literal equation is kind of like rearranging the equation in a way because you're not getting a one numerical answer. You're getting a different equation with your variable isolated, the variable they're asking you to do. Okay, so let's change colors. We'll go to blue this time. And this time we will do this volume of a cone formula because we have been working with finding volumes of cones. So I'm sure you're familiar with this formula. But this one, they're asking us to solve for R, which means I need to isolate my radius, my R. We don't know the value of V. We don't know the value of H. The only thing we can do is put an approximation of pi in. So we have to think about what is happening to our variable, okay? 1/3 is being multiplied times the pi. Pi is being multiplied times the radius squared. And then that is being multiplied times the H. So all of these variables in this fraction, it's all being multiplied together. And the inverse of multiply is divide. So I'm just going to do it one at a time. I'm going to take my 1/3 and I'm going to divide it by itself to cancel that out, because that's going to give me a 1, and 1 times pi r squared h is just pi r squared h. And again, I need to do the same thing over here. I need to divide by 1/3. And similarly to what I did over here, if I have a v and I'm dividing by 1/3, I am really multiplying times its reciprocal, 3/1. And when I do that, I will get 3v over 1, which is just 3v. So when I rewrite my equation here, I will have 3v on the left side. On the right side, I will have pi radius squared times the h. Okay. Now, I'm going to use my commutative property, and here's why. Because if I move my h over here next to the pi, I can just divide by both of them at the same time rather than doing it individually like I was doing before with the fraction. And I'm going to do that because I know if it's multiply, I can move things around and still get the same answer. 3 times 5 is the same as 5 times 3, right? So I'm going to use that commutative property and just rewrite this equation like this. 3v equals pi times h times r squared. And the reason I did that was so that I can go ahead and divide by both of these at the same time and just eliminate both of those things on the right side of my equation, because pi times h divided by pi times h is 1, right? And then when I divide this by pi times h, I can't really figure out the entire value of that because I don't know what v equals numerically. I don't know what h equals numerically, and I really don't want to approximate pi right now because I don't know the other values. So I'll just leave it as the symbol because the symbol is easier to work with. So what I essentially get is 3v. Let me just put a line over there too so you can see what I did. Okay, 3v over pi h, pi times h, equals r squared. Now, the only thing left to get rid of is that square, that exponent that's on my r, that's on my radius. And the opposite of squaring a number is to take the square root. So I need to take the square root of both sides basically to finish this out. I'll do that on this side of, I'll draw a line here and we'll do it over here. So if I do the square root of this side, nothing's going to change. I'm just going to have that little square root symbol over it because I don't have the values. So I can't really find the square roots of all those. And if I find the square root of r squared, it will become an r because r times r is r squared, right? So basically this is my answer. R is equal to 3, the square root of 3 times v over pi times h. And so if you were trying to solve a word problem concerning volume and they wanted you to find the radius, you could rearrange the formula into this and just fill in the volume and fill in the height and get your radius by just like multiplying 3 times the volume, dividing it by pi times the height, and then finding the square root. That's one way to do it. And so it is useful to be able to rearrange formulas and to solve literal equations. Here's one thing that we're going to do in Unit 3 coming up, and that is turning linear equations from standard form into slope-intercept form. So I'm going to explain what that looks like. Linear equations we're going to work with when we work in our function unit, and that's our next unit coming up. So you have never heard of this before, but linear equations can be written in different forms, and sometimes we need it to be in slope-intercept form. And there's reasons for that, which I'll get into in the function videos and in the linear equation videos that I'm going to make. But right now, we're just learning how to turn, an equation that's in this form, the standard form, meaning ax plus by equals c, where a, b, and c, the ones I just underlined, are numbers, right? And we want to turn that into the slope-intercept form, which is y equals m times x plus b. And m and b are numbers, okay? So if you look at this, you can see that if I just use commutative property to move this 2x over here and move my 3y over here, because we know that commutative property works with addition and multiplication. 2 plus 3 is the same as 3 plus 2, right? So it doesn't matter which way I have it written. But you can kind of see now that I've moved it around a little bit that this is a standard form equation. You have a times x, and a being the 2, plus 3 times y, 3 being the b, equals the -1, which is the c, okay? And we want to solve for y. And when we do that, we'll have our slope-intercept form. Okay, so what's around our y? This is just a normal literal equation if you think about it. We have a 3 being multiplied times the y, and then we have a 2x that's being added to the y. So we have to get rid of the add subtract first before we do the multiply divide, right? So I need to get rid of this 2x. And to zero that out, I'm going to subtract it because it's a positive 2x. And it's being added, not multiplied. A lot of kids want to divide there, and I'm like, why are you dividing it? It's not being multiplied times your y, right? It's 2 is being multiplied times x, but if you divide by 2, you're just going to get rid of the 2 and leave the x. We want the 2 and the x to go away, so that's why we're subtracting 2x from 2x. And whenever I do that on this side, subtracting 2x, I can only write it like this. I can write it as -1 minus 2x because I technically can't take an x away from something that's not an x, right? Like terms, when you think about that. Okay, so if I rewrite this equation, this is now gone. I'm left with 3 times y equals -1 minus 2x. Now, I'm not quite finished because I still have this 3 over here that I need to get rid of, and this 3 is being multiplied times the y. So I'm going to just divide by 3. That will make that a 1y. And then when I divide all of this by 3, I want it to look like this equation. So what I want to do is actually write it in this way, because you can separate this. You can separate that, okay? This is the same as up here, what you're looking at right there. -1 divided by 3 minus 2 divided by 3x. Okay, that's what you're looking at right here too. And this looks more like this. The only difference is, I'm going to write it right here. I can move these terms around, not using commutative property this time, but just using my knowledge of negative positive numbers. And now I have exactly this. I have exactly the y equals mx plus b. So the reason I made it look like this is because on this y equals mx plus b, the x term, the term that has a number multiplied times x, that comes before the b on this one. So I just basically moved it to the front. And that minus goes with the 2 over 3. It does not go with the 1/3. That minus has to go with that term. That's why I made it a -2x over 3. Okay. And then this negative here goes with that 1/3 as well. So I had to make it minus 1/3. Okay. Because that's just the same as a plus negative. So this is right. This is more right if you're trying to make it look more like that. Okay. So hopefully that helped you learn a little bit about how to manipulate some geometry formulas. And now it's time to review. I might make another video on just moving standard form to slope-intercept form. So remember that we solve for a specific variable when we solve linear equations. And remember, we use the usual steps in the DCMAM method for solving equations when solving literal equations. But we often represent our answers in each step with variables or a combination of variables and numbers. Remember to use properties of numbers such as the commutative property if it helps you to solve the literal equation. Also, concepts like how to divide by a fraction, keep, change, flip, those kind of things. Remember to simplify any fractions around any non-terminating decimals that you may have when solving literal equations. And remember that solving literal equations is important when solving problems relating to geometry formulas and converting linear equations from standard form into slope-intercept form. So hopefully you learned a little bit about literal equations today. And now it's time for me to say, great job, y'all. And don't forget, I know this might be a little confusing. You might have to watch it a couple of times and work with these literal equations for a little bit to get more into the hang of it. But the more we practice, the more we grow. And I believe that you guys can grow in this and get better at this throughout time. So don't give up and keep on trying. And now it's time for me to say, it was lovely teaching you math today. Bye.